Welcome to Mechanics of Composite Materials. Today we'll be discussing how we can characterize the fundamental properties of composite materials. And a lot of the images I'll be showing in this particular lecture were adopted from the Engineering Mechanics of Composite Materials. Second edition, Isaac, Daniel, and Ori Ishai. So when we're trying to determine whether a structure is going to break or I want to design a structure so it doesn't break, it becomes very important to understand that to predict failure, we may use either strain or stress. And so when you apply a load to a structure, that loading that you apply to that structure is going to cause point by point within the material is going to cause a stress and a strain. And one of the most important things that we need to discuss when it comes to composite materials is that when I apply that load, that's going to cause a stress or a strain and a strain, but that the stress and strain is related through this constitutive relationship you see on the screen. And this matrix is called, in this case, it's called the compliance matrix, and it's actually fully symmetric. You're going to observe here that you have E11, E22, E33 in the diagonal. In and you're going to have also shear modulus. Now, in isotropic materials, when you're dealing with isotropic materials, you only have two constants that you have to worry about: the Poisson ratio nu and the modulus E. That's it. That's all you have to get. But when you're looking at a orthotropic material, for example, which has three planes of symmetry, um, in reality, you're going to have nine independent constants. But because this matrix, in addition to that, this matrix, this compliance matrix, fully symmetric, you can create this relationship in that nu ij divided by eii equals nu ji equals e divided by ejj. And you may ask me, what is E11? Well, E11 is a modulus along the one direction. E22 is a modulus transverse to the one direction. E33 is a modulus perpendicular to the one and two axis. And then when I look at the Poisson ratio, we need to fully understand what the Poisson ratio really means. You're basically loading in one direction and measuring the strain, how much percentage contraction strain you have across that loading direction. So I apply a load in one direction, how much percentage contraction I get in the second direction. So I want to look at the strain, that ratio of epsilon 1, epsilon 2 will tell me a lot about that Poisson ratio. So a lot of this stuff can actually be measured. We can measure all these properties. And so the relationship of stress and strain, we find that through material characterization, which is a lecture today, right? So there's three modulus, three Poisson ratios, three shear modulus. And what I want to point out is that for depending upon whether you're dealing with a unidirectional material or you're dealing with a plane weave, you're gonna have different answers, right? So what I mean with that? So there are various options when you're dealing with composite materials, and I want to really explain to you what is going on behind the scenes. So let's look at unidirectional materials. Unidirectional materials, I'm going to have a composite. Reply is going in one direction. And in this direction, I'm going to measure E11. Okay. And in this direction, I have E22. And in this direction, I'm going to have E33. And I want you to notice how I must have for unidirectional composites, I must have that E22, that this modulus must be equal to this modulus here because it's transverse to the fibers in both cases. It's transversing the fibers in both cases. Now, since the fibers are going along the one direction, I'll expect E11 to be greater than E22. Has to be because E11 is aligned with the fiber direction, which is that direction. and the fibers are stiffer than the matrix. So if I were to load it up in this direction, and then the fibers are going this way, I'm loading up across the fibers, which means the fibers are going to not contribute as much modulus in the two direction compared to two. So I'm calling this the two and the three and the one. And so E22 must be equal to E33. Now let's examine the Poisson ratio. So I load up the sample in the one direction, and I have contraction. I want to measure contraction in the second direction. Well, very similarly, I will notice that if I apply a load here, and I'm examining what's going on in this direction, which is what Poisson ratio really means, you can see I'm examining across the fibers. So nu 1, 2, interesting. So let's look at nu 1, 3. If I apply a load in this direction, in the one direction, then I measure the contraction in the third direction. Now notice that whether it's if I'm measuring the contraction in the two or the three direction, that in both cases I'm measuring across the fibers. So it makes sense then that nu 1, 2 equals nu 1, 3 in this scenario. So I hope that's clear. Now when I look at nu 2, 3, that's an interesting story, right? The fibers are going this way again. I'm applying a load in this direction, in the two direction. And yeah, so I apply a load in the two direction, and I measure the contraction in the third direction. Well, in that scenario, I can see that I'm applying load across the fibers, but I'm measuring the contraction also across the fibers. So very clearly, nu 2, 3 should be different from nu 1, 2, and nu 1, 3 because nu 1, 2, and nu 1, 3, the load is applied across along the fibers. You're measuring the contraction across the fibers. While in this case, I'm applying the load across the fibers and measuring the contraction across the fibers. G12, by the same argument, G12 and G13 are very similar. They're equal. And why is that? So if I examine that carefully, again, so let's look at that one. If I apply if I look at G12, G12 is this plane here. And the G12 plane contains fibers and contains across the fibers, right? I'm going across the fibers and it's along the fibers. G13 also has a component of fibers and also across the fibers. You may ask me, what do you mean across the fibers? Well, if I look at the cross section, I have fibers going there, right? And this is the third direction. So I'm going across a fiber, obviously, right? So we want to keep that in mind. And so G12 and G13 must be equal. Now G23 is different. G23 is actually G23 is actually this plane right here. That plane, I'm going across the fibers in both directions. So G23 must be different from G12 and G13. Now G23 may be hard to measure. Typically G23 can be looked at as a percentage of G12 and G13. You can make an assumption there. People have done it. Nu12 and Nu13, since it contains fibers, typically, I'm not saying it's always the case, but if you don't have test data, it's usually safe to assume that Nu12 will be close to 0.3. And since 2,3, the plane 2,3 is going across the fibers, then it's resin dominated property. And resins typically are in the 0.4 value. I'm not saying those are the values, but with lack of better testing, these are an approximation that you can think about. So these are some ideas for you to keep in mind as you work this area of expertise. Now when I look at plane weave composites, so I have a plane weave composite. Here's my weave. So plane weave composites, I have fibers going in both directions now. So it makes sense that if I have even number of fibers going in each direction, that E11 must be equal. So if this, say for example, that this is the one direction and this is a two direction. Sorry, this is a two direction. This is a third direction. Okay. Um, and I'm actually drawing this incorrectly because in reality, this has to be one. This has to be two. These are the coordinate system I'm using. And I can see here that E11 must be equal to E22 because I have fibers going in both of those directions. And I will expect that to happen. Now, E33 is across the fibers again because it's perpendicular to the plane where the fibers are contained in. So therefore, E11 equals E22, okay? While E33 must be different. So I hope that's clear. Um, we also have, in this case, I look at no 1, 2. No 1, 2, if I pull on the fiber, I'm measuring along the fiber again, because if I pull on the one direction, I'm measuring the contraction in the two direction. Now, since I have fibers in both directions, I'll expect nu 1, 2 to be different from nu 1, 3 and nu 2, 3. Why is that? If I apply load in the one direction, I'm measuring contraction in three direction. That's across the fibers. If I apply loading in the two direction, I'm measuring strain along the two direction, measuring the contraction along the three direction, which is across the fibers again. But nu 1, 2 is different. Nu 1, 2 is applying the load along the fiber, measuring the contraction along the fiber again. So we covered that one. Now, what's interesting about nu 1, 2, I wanted to look at the top view of this. There's a top view. And I didn't have any resin. No resin. For a second. So if I apply a loading in this direction, I'll expect very little effect in this direction. So if there's a one direction and there's a two direction, I'll expect that if I have fibers going in both directions, if I apply loading in the one direction, the two directions probably unaffected. So typically, I'm not saying it's always the case, but nu 1, 2 is close to 0.5 to 0.1. If you don't have test data, you could probably make that assumption. And typically it's being found that nu 1, 3, I apologize, is somewhere between 0.3 to 0.4 when you do testing, okay? Other composite architectures may require characterization of all 9 independent constants, typically done through extensive testing. You can also use a micromechanics approach where you're actually not doing any testing, but you know the properties of the fibers and the resin, and you model a finite element model of the microstructure to derive the properties. That's one approach that has been used successfully. A second approach is actually to use a microstructural software like TextCAD. And you'll see that later in some of the work you'll be doing. So when it comes to composite materials, we'll typically will use a building block approach for testing composites. We want to start at the coupon level using coupon level testing. And the coupon level testing is intended to help you characterize the properties at a very basic level. Once you have that very well characterized, you can then move to element testing. Then you can add little more elements to the test by adding holes and things like that. And you will complicate it all the way up. And the idea is that when you arrive to full scale test, like a whole airplane, for example, a whole airplane wing, that you've done all the homework. You've done all the homework to ensure, you did the homework to ensure that you know how the full scale is going to behave. You don't want to go into a test of the full scale only to have the full scale fail on you. You want to be successful. And to be successful, that means understanding the properties at the basic level, at this coupon level test. The building block approach then requires understanding. So, for example, with metals, you find the strength, the yield, and stuff like that. Well, with composite materials, you're going to generate basis allowables that you're going to use in the design process. And it's going to help you understand the critical failure modes. You may have to test at various environments like temperature and moisture. You may have to design and test specimens to then verify analytical predictions. Also, testing is important because it helps you understand the quality control. And finally, you want to repeat this as needed because that's of great importance. And testing can be quite expensive, so you have to be balanced about how you go about this. So let's look at the types of testing that will be part of the qualification plan. So when you're actually developing a qualification plan for a composite structure, what kinds of testing you need? You need constituent testing. And what I mean with that, fiber testing or the matrix testing. You have lamina testing, laminate testing, and then you may have to do structural element testing. And once you get to that point, you want to do statistically based testing, which means you want to figure out how many coupons you need. You need to then look at when is appropriate to mix and match test data to look for equivalences. You can't test everything perfectly at every temperature, but you can then draw some conclusions about how you can mix statistics in a useful way. You want to look at qualifying by similarity as an approach, and that requires looking at the functional performance, environments, design, manufacturing, and test requirements. You also look at tagging coupons, and then finally you will be looking at test methods um, for composite materials because the ones for metals may not be directly applicable. In a lot of cases, you may not be able to test perfectly like you would like to do, and so as a consequence, you have to look at test like you fly options. Basically, are you doing a good job of testing on the ground and mimic the response in flight? That is the goal. So, what are the test issues? Some of the common test issues for composite materials. We have the influence of the constitutive content on the material response, anisotropy, specimen conditioning, alignment issues, multiple failure modes, shear stress response uncoupled from normal stresses, sensitivity to specimen preparation, failure to maintain control of testing processes, and those can actually compromise the data. So you have to be very careful about what you're doing. That's extremely important there. Another thing I want to point out that's of great importance is that when you're preparing samples, it's important to pay attention to the details because the results from the testing can be very influenced by the 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 way you test. You know, if you have misalignment issues, you may predict failure a little bit earlier. If you have multiple failure modes that complicate the problem, you really want to understand that. And then you may have situations where um, you may compromise the data because you didn't really understand what you're testing. And so that's why it's so important to really pay attention to what we're doing in this and now in the testing uh, area domain. And testing is very important in composites. It can save weight or it can actually increase weight. Let's look at testing of composites. You're going to have fiber dominated properties. And when I say fiber dominated properties, what I mean there is this. If this is my lamina, this is one, and I keep drawing it around. This is 1, 2, and 3. And the reason I'm making the mistake is because of the right hand rule. I want to be able to meet the right hand rule. When I look at the fiber dominated properties, you have the in-plane strength and the in-plane stiffness. So you're going to have to look at that in-plane strength and in-plane stiffness. And those properties tend to be the one that reside in the 1-2 plane. So that's where you're going to find those. When I look at resin dominated properties, I'm looking at compressive strength, shear out of plane properties, meaning, so for example, what I mean with that. So I have 2 adjacent plies, and these are my fibers. Resin dominated properties, anything that's exercising that resin. Typically, compressive strength is going to do that. Out of plane properties, so loading in this direction, shear that may break 2 lamina together, they're together. That's resin dominated. Testing should be geared to measure a specific performance, we don't want to just test, right? Just to test. We want to really understand how the data will be used, how the data will be processed, and why I'll show you later. But if we don't pay attention, we may cause some weight penalties that may not be intended, and it will come up later as I discuss it more. We want to pay attention to the large stored energy that could be there, understand the test parameters prior to the test, and really, in some cases, you may even need close to 100 tests to really characterize a composite completely correct. In composites, that's why it comes with a lot of baggage. When you adapt composites for a particular application, you're looking at more testing than for metals. So here's an example of guidelines for testing of composites prepregs. And here you can see a number of tests. You have a resin content. So that's basically measuring how much resin you have in the composite. And you also look at fiber aerial weight. And that's typically done using the ASTM standard, D3529. And so I encourage you really to go through this list and download this standard so you can study what it talks about. But that same standard is also used to measure insoluble content, for example. And it also helps you understand, the knowledge of these results is useful. It helps you understand the manufacturing processes. It helps you understand where volatiles content is consistent and not critical to the process. These test methods are limited to this type of structures that we're talking about. And it is a good testing, 3529. You also have the volatile content, the resin flow, how well that resin flows, how long it takes the resin to gel. So that's ASTM 3532, and you can see they're in order because they're interrelated. They really help understand that material property there. And resin gel time should occur. You want gel time to occur shortly after resin pot time expires. And so the gel, this resin gel time, understanding that does plays a role in how that composite performs. You want to look at moisture content, ASTM D4019, tack, drape, percent cure, how tacky that resin is, insoluble content, DSC, we talked about that, rheology, DMA, HPLC, and IR. So these are standards you can download and take a look. We also then have guidelines for Lamina testing. Now, here I went from prepreg, understanding the prepreg behavior, which is really a fiber prepared within the resin, to now talk about Lamina testing, which now we're looking at microstructural behavior, which is a little bit different from what I discussed in the previous slide. Here we're looking at moisture conditioning, glass transition temperature for wet and dry. You can look at density, cured ply thickness. So when you cure a composite, the ply thickness may not be what you thought. So you can actually measure that using that standard. Fiber volume, you can measure the fiber volume content, the resin content, the void content. And then you can look at moisture diffusivity. You can look at coefficient of thermal expansion out of plane, coefficient of thermal expansion in plane, and then the thermal conductivity, specific heat, and the thermal diffusivity. And I'm giving you all the ASTM standards, which is awesome because you can now go and you can download them and you can understand what this is about. Okay, without I'm giving you some guidance, so you have to go from scratch, try to figure out what kinds of tests you may need to fully characterize a composite from scratch. And so I hope you're finding that valuable. And so we then have to test the micromechanical properties, and the micromechanical properties is a whole set of tests. And not all these tests need to be performed, but typically enough to predict the behavior in the environment that they will be used. You have to assess the cost-risk balance. They need to be assessed. The type of processing may limit the type of test configuration available. For example, a filament wound structure may need a variation uh, to measure tensile test, for example. A basis to B basis allowable will have to determine how many sample sizes you need. So that's of extreme importance. And here you can see on this table a large number of tests. So the first three typically are used for process controls: in-plane shear, short beam shear strength, and 4-point flexure. The corresponding ASTM standard is on the right-hand side. Then you have to measure the lamina properties, so the in-plane tension, and I'll go through some of this. In-plane compression. So you're measuring the performance of the composite in the tension, and then also in compression, which can be different. Um, Typically, strength in tension tends to be higher than compression. Compression, the matrix had to take the bulk, some of the load, and the matrix is not as good at taking compression. Then you have in-plane shear, you have out-of-plane shear and tension, open hole tension, field hole tension, open hole compression, field hole compression, single shear bearing, double shear bearing, bearing bypass interaction. You also have fastener pull-through strength, compression after impact testing, and then you have a slew of fracture testing that may need to be done and completed, along with fatigue testing, and then bearing fatigue. So these are kinds of testing you may need for a particular application. You may not need them all, but you can see the number of tests I need for composites compared to like same metals. The Composite Materials Handbook 17 test has some of the tests listed. And so what I've done is shown you a zoom where that came from, um, and just to keep you apprised about the things in there. The standard test method for tensile properties of polymer matrix composite materials, which is the D3039, this test method is intended to find the modulus, for example. It can also give you strength. The standards provide very detailed test parameters. If you download one of these, it's going to give you a lot of information. It's going to give you inferences, material sample prep, gripping, system alignment, edge effects, angle plies. It's going to have a lot of information that you can go through and assess. The tensile test typically is going to have two extensometers to measure strain and bending. We typically use LVDT technology, which is excellent. Displacement measurements are done, and the crosshead monitoring is not typically appropriate for calculating strain. And the reason is because you have some compliance from the fixture around it. So that's why you want to use LVDT, a gauge there, to measure what is going on uh, in terms of deflections, right? So that's what the LVDT is doing. Okay. And if you don't know what an LVDT is a linear variable differential transformer and allows you to convert an electromechanical transducer to rectilinear motion. It allows you to give you how much deflection I get from that change. So again, we don't want to rely on the crosshead deflection. More reliable is LVDT. So the ASTM 3039 tensile test, you apply a longitudinal test, 0 degrees. At the 0 degree, you're going to have 6 plies there. And the output is the longitudinal modulus E11. The Poisson ratio can be calculated. So if I'm loading in one direction, I can measure the contraction in second direction. I'll plot the strain epsilon 11 and epsilon 22, and then determine the ratio of epsilon 11 and epsilon 22, and that'll give me nu 12. The longitudinal strength can also be calculated. So if I apply a load, I can take it to failure. I don't get the nicking that you see in metals. I'm going to get a brittle type failure. These kind of materials will fail in the 1% range, 1.25 to 1.8%, most of them. And so as a consequence, you don't expect to have a lot of plasticity at all. Longitudinal test uses 90 degrees, 8 plies, and the 90 degrees are 8 plies. will give you the e to 2, the modulus in the 2 direction. And you can see here the fibers are going across. Right. So you have that. I apologize, they're not going across. But my point is that for the 90-degree test, let me draw it. The fibers are going this way. So I'm obviously measuring E22, nu 2, 1. And notice from this test, I'm measuring E11 and nu 12. And so I already told you there's a relationship of this. And so I can actually experimentally verify that this is correct if I do the test correctly. I'm also able to get the strength along the fiber, but also across the fiber in this direction, across the fiber. So that's great. And I can also get the strain to failure. These are the data we're going to use later to predict failure. I need this data to be able to predict failure. These are some of the requirements in the tensile test requirements that are discussed extensively. They provide you a table with specimen geometry recommendations. They provide you the width, which there what we're talking about. So for the 0-degree test, there's a width they're recommending. For the 90-degree test, which is plies going this way, there's a width they're recommending. They also give you tab measurements. How big this tab is also discussed. So what we have here is the ability to use this table right here to determine specimen configuration. So we discussed tab length, tab thickness, and then we can look at the tab bevel angle. So those are the kinds of things that they're going to specify. We also have tensile specimen geometry requirements. You have coupon requirements, and then you have tab requirements. And they explain a lot of things here through this process. What are the typical failure modes you could have in a tensile test configuration? You can have various failure modes. And to understand it very well, what you want to do is to understand these characters here at the bottom. LIT, for example. So L here means that's first character. And so you go to this table and explains to you how to use it. But L here means lateral. I here means inside grip tab. And then the third character provides a failure location. So here in this case, LIT, T means top. So here we fell at the very top. Here we have a failure at the grip, which is not really desirable because that'll give you a lower strength potentially. Here you have a failure at LAT. What is that? Lateral at grip. And then also we have top. And then you have DGM, which is, again, these are various, this will be like delamination. So you have delamination there. And that's in the gauge section. That's what the G is there. And M there means middle. And that's not desirable. We don't want to see, we'll rather not have DGM. And then we have LGM. L is lateral, gauge, and middle. That'll be a very nice failure mode if we can get there. We have SGM, which is another kind, which is splitting, not desired. AGM, angled, and then XGM, which is explosive and looks broomed. Usually under compression, you may see this as a consequence in some cases. Let me show you an example of what the data summary may look like when you do the test. So when you do the test, you're going to instrument this. with a strain gauge here, typically we put a strain gauge back to back. So maybe one here. I apologize. One here, one here, and one here. So strain gauge on either side. That'll give you the ability to measure any bending going on during the test. And in these cases, we can see here I have the front extensometer, the back extensometer, and I have the average value. I can calculate the average, and if I have strain gauges back to back, I can look at deviations due to bending. In this case, when you apply the loading, it's going to be at a rate. So in this case, it's being done at 50 mils per minute, so very slow. And a linear regression will be done to calculate modulus, for example. And typically, you don't want to do it too high or too low. Too high, you'll start already getting some damage. And here's telling you how much percentage bending I'm getting. And this tells you, how good the test is. And here you can see the tensile strength. You can see there's an average value you can calculate. And we also have, the average value, and then we have the standard deviation. So those two may be needed later in the calculation. So I have the average, the standard deviation. I need to come up with an approach to calculating the allowables later. But again, this piece of information is highly important. We have to calculate the tensile modulus and the tensile strength, and they both become important. One can make an argument that this looks out of family, potentially. We don't know until we do statistics. Longitudinal compression testing typically involves testing the C36499 sandwich column, and that allows you to induce loading into the strain gauge section. And the output is going to be E11 modulus in compression, longitudinal strength in the compression regime, and also strain to failure in the compression regime. Another approach can be used to test is to use the 4-point bend test. The 4-point bend test can be very, very successful. And what I'm doing there is I'm applying a loading configuration here and here. Is getting reacted here. And if you draw the free body diagram, you're going to find that in this center section, we're going to get pure moment M. And you recall that stress equals MC over I. So you get compression at the top, tension at the bottom of that beam. So it's an excellent way to measure compression modulus by putting a strain gauge there. And you can also then, if you put a strain gauge there, you can measure strain. And because you have stress, you know what the stress is in the outer fibers, because of MC, stress equals MC over I. M times the distance from the neutral axis to the outer fibers, divided by I, the moment of inertia, you can calculate stress. And since you know strain, you can then relate the two to then calculate modulus. You can also test it to failure as well to then get the compression strength, because this top is going to be in compression. Okay. So what are the issues with this compression test? You have uniformity of the stress state. Tabs can be a stress concentration. Results are sensitive to variability in sample tooling. There's machining accuracy issues. The material factors can be fiber waviness, misalignment, fiber volume, and then there's a number of test approaches that are available to look at that. And I showed one of them, which is the IIT Research Institute, but there's other ones that can be looked at. The D3410 is shear loaded, and it can be looked at. This is from the Illinois Institute of Technology. That's what this stands for. Additional test methods are the D695 end-loaded, that's a Boeing modified, you can look at that. Wyoming end-loaded site support, the block compression, the Royal Aircraft Establishment, and then the block compression. These are different ways to measure that modulus. And all we're trying to do, just so we don't lose perspective, we're trying to populate this compliance matrix. And we're also trying to get the strength to failure and strain to failure, because those will be used later for failure predictions. It's important. Very nice. This is very practical stuff that you're going to encounter. Each of these tests is going to have a benefit and some disadvantages, and you have to look at which is the best one for your application. The compression D3410 test provides the ultimate compression strength, the ultimate compression strain, the modulus, Poisson ratio, and it provides the transition strain. So it's giving you a lot of data, and it is one of the several competing technique standards that you're going to have to look at. In the D3410 compression test requirement, you're looking at applying a uniform compression stress in the gauge area. And you're applying compression in this regime. Here is the compression test requirements for that sample. I don't want to go into extensive detail. The point I'm trying to make is that each of these standards are going to have a number of requirements, and a lot of them are driven to, they already know what matters and what doesn't matter. We want to avoid order buckling. So, okay, as a consequence, you can design a sample in such a way the buckling is not a problem. But here is what you see that the recommendations are. And you can see here minimum required thickness, expected compression strength. Doesn't mean you're going to get that, but it's giving you some information about how to go about the testing and what expectations you may have. The compression testing failure modes can be complex. You can have some sort of transfer shear. You can see some transfer shear there. Brooming, like that one. You can have clean failures as well, harder to get. Most of the time, you're going to see this kind of stuff, most of the time. And then you may have grip failures that are not really good. And that's why you want to picture every sample. You want to picture them to understand what was the failure mode, what happened, and what can be done. There's a number of test approaches that are available, and it is for shear in testing, and it is difficult to get uniform shear in the test samples. Some tests get shear strength, not modulus, and vice versa. Here you can see the list of tests that are typically recommended. Now, this one is an excellent test, the isopescu D5379. It does a great job of inducing a nearly uniform state of stress into that gauge section, and also allows you to get modulus and strength. Very good test. And here you can see the other test, short beam shear, plus minus 45 degrees, and this in error. What we want to say there is isopescu. Two rail shear, three rail shear, double notch shear, tube torsion, and notch rail shear. One of the most common tests that are done is the in-plane shear. This one here, which is a 3518 standard. And what that is, I'm putting fibers now at plus minus 45, like that. Crisscross. You can see that. Well, it's not, you cannot see it there, but you can see what I'm saying. So that's a 45-degree angle from the loading axis. And so you can see there that I'm applying a load in this direction. I'm going to measure the strain in this direction and this direction. Notice I'm not measuring the strain along the fibers, but I'm measuring the strains in the loading direction. I can then take that, subtract it. I know the loading applied. I can get G12. And so that's how you do that test. Typically, these tests will give you shear strength, shear strain, modulus, and it's very rare it's going to be linear. It's going to typically be nonlinear. Typically nonlinear. The in-plane and out-of-plane shear stress going after the fact that when you have plies. So what I'm looking for there, in-plane shear is going to give you the modulus in the in-plane direction, similar to this. The problem with this test, the in-plane shear plus minus 45-degree test, is that as the loading occurs, the fibers will try to scissor so that now the fibers are more oriented along the loading direction. And I'm exaggerating. So I went from 90-degree to at a steeper angle. And so now the fibers start to contribute to that loading. And so it tends to overestimate strength. Because of the scissoring effect. The in-plane and out-of-plane shear test I'm showing you here is actually a very good test. And that's the isopesco test, which you can download. And that here you're trying to get the shear modulus in this section. And while there's a notch here, that actually does not act like a stress concentration. It does a really good job of providing uniform shear in that gauge section. In-plane shear modulus can be measured. The typical ply layup is 90 degrees. You can get shear modulus, strength. You can get out-of-plane shear modulus, and so forth. So very good test. Here you have to put a row set at plus minus 45 with respect to the longitudinal axis. And a lot of people put a strain gauge in the front and also in the back. So back to back. This test is mostly done for quality purposes. So you're really looking for in-family data, looking at the behavior for that purpose. And what is this test trying to do? So this test is looking at material quality. So if you have bad material quality, then you have the propensity of having more cracks here in these areas. So if you have low quality material, those are going to grow quicker, and cause a problem. But important to note is that this is used for quality tests. I've seen people try to use it for characterization, but the problem is that the fibers are oriented this way. And so think of a hammock. A hammock, right? A hammock sounds good right now. If you look at a hammock, is these fibers really carrying the load? So if I exaggerate, this beam is going to bend like this. The fibers are going along here. So the fibers are going to carry some load. And that's why it's not a good test to get allowable, strength allowable for design, but it's a good test to check for quality, the quality of the material. Why is that? A lot of testing has been done, and you can see as the void content increases, you can see the impacts on the short beam shear. You can see that's dropping as well. So the void content can affect interlaminar shear strength and other resin dominated properties. If I want to measure out-of-plane tension test, and that means these are my plies, and I measure modulus going that way, and the strength going that way, I can do that. And all I have to do is fabricate a coupon that has a shape like an hourglass. And not only that, now the fibers are going like that, across like that. And so if I apply a load now, I can get E33, Nu13, the strength, F33, and the out-of-plane elongation to failure. So this is a quick summary of the types of tests you may see: longitudinal tension, transverse tension, longitudinal compression, transverse compression, that's important, in-plane shear, And as you can see on the right-hand side, you can see the properties you can get from each of these tests with a diagram in the middle. You can see here I can get elastic properties for a lot of them. And also I can get shear strength for a lot of these tests. And again, you have to decide which is the best test for your application. But these tests are required to characterize the material. Other tests include interlaminar shear. We talked about that. Now this is used for quality control. I talked about that one. I talked about this one, autoplane thick loading. You can also apply compression loading successfully. And then through a thickness shear, which is similar to Asopescu test, basically. I recommend reading this FAA article, AR00/47. It talks about material qualification and equivalency for polymer matrix composite material systems. You also may have to do composite material qualification. And I cover some of the standards. You have to do molecular weight, distribution, how tacky the resin is, and so forth. So when you do a test, you have to really test at all critical operating environments and moisture. Cold temperature dry, room temperature dry, elevated temperature wet, elevated temperature dry. And that will allow you to qualify the material for equivalency. You can see here that we have more coupons at room temperature than we do at the other conditions. And what you see here is a number of samples and number of lots. So the first one here is number of lots. This is a number of samples. So when you do testing, you're going to do a bunch of tests. We want to make sure that you carefully measure all the samples prior to test, verify the correctness of ply angles, take photographs of all failed samples and all failure modes. They all should be consistent. If there are some issues, you have to figure that out because you don't want to include data that's contaminated by a failure mode that's not of concern. Because what that's going to do, if it results in a lower strength, it's going to pull the allowable strength to a lower value, which means now you have to add more weight. So you really want to understand the failure modes in the sample, like I showed earlier, like the brooming and stuff like that. You want to have a sufficient number of samples because if you don't, you'll see the consequences later. We recommend testing from at least 3 lots, and it can change from program to program. And you should eliminate outliers if you have good justification. And I'll go through the outlier process on how to remove it. So we want to eliminate outliers because they can bias the data the wrong way. So to do that, we want to look at the maximum normed residual. And what that is, let me show you how to do this. You're going to calculate, you're going to have all the data one by one. You're going to calculate the average of all the data. So that's easy. That should be fairly easy to calculate the average of all the data. I apologize for that. So you have each of the data points. You want to calculate the average of all the data. Take the absolute value and divide it by the standard deviation. And you're going to do that for each of the data points. Now what you want to look at is you want to ask the question, is this MNR value greater than this a critical value? That critical value comes from this table. That's small. I see that small. But if you have 20 samples, you come here to 20 samples and say, okay, it's 2.708. So then if MNR is greater than 2.708, then you're going to have to consider that an outlier. Now, listen to the words I use, consider that as an outlier. Why? You cannot just throw it away. You have to really investigate it why. Maybe it's legit. Maybe that data point is actually legit and it's important. And you have to have good justification. Now, say the low sample, that outlier was because it fell at the grip. Well, that's good justification. The grip may have contributed because the grip can be a stress concentration. So keeping in mind, um, these calculations of extreme importance in when we're trying to process the data. Now let's look at a couple examples for outlier. In this case, we have the raw data given here. And if you calculate the average, you can look at the average and then look at the number of samples and then determine whether MNR is greater than the critical value. In this example, it happens to be that the critical value is 2.652. MNR, this one right here, is greater than the 2.652. You can see that there. As a consequence, that could be considered an outlier. We look at it and we find that there's a problem with the sample. So yes, I can drop it. And notice how that's nice, because if I can drop the 58, look at all the other ones. The other ones are really nice. They're higher. But if I kept that 58, it would have pulled my average down. If it pulls the average strength down, not only there's scatter in the data, it pulls the statistics also, the standard deviation higher, which pulls my strength allowable to a lower value. And so that means I have to design a structure even more robust, meaning more weight. And so you may have lost the whole point of using composites, right? So you want to do that for each of these sets. And notice how I have CTD, RTD, ETD, ETW. I'm showing you that all the set of data here in one place so you can see all of it at once. How many test samples are needed? The statistical models are used to approximate the population from which the data is sampled. How is the data distributed, whether it's normal, variable, the degree of how you can reproduce it, the variability in the property be measured, variability in measurements of the property due to the test method, and so forth. You can see here the number of samples increased, and what is the B basis doing? So let's look at that. And I'll calculate, I'll talk about the basis value, but here you're going to have the average here, and this is a statistical value, depends on the number of samples. That's your standard deviation. And I'm going to design to the basis value. There's two basis value, the B basis and the A basis. And these are needed. These statistical models are needed because I'm going to have variations, and I don't want to design to the average. What if I have material points in a structure that behave more like a lower value than the strength, the average strength? That'll be a problem. So I have to design to some statistical value here. And that statistical value that I'm calling A basis or B basis is going to be equal to the average minus some factor times the standard deviation. So that's the important point to really understand. And notice how the number of samples, increase in number of samples, lowers this K value. So that's interesting. Let's look at that carefully. So the basis value, mean, minus a scatter factor, and I'll give an example later, times standard deviation. Now, if I have a lot of samples, I have 80 samples, this K becomes 1.56 if I have 80 samples. If I have 5 samples, the factor is closer to 3.4. What does that mean? It means that these factors are multiplied to a standard deviation and then subtracted from the mean. That means that the lower number of samples I have, that basis value is going to be lower, which means my design is heavier. So you have to keep in mind that you have to find the right balance. If I want a light design, I want to have a lot more test data. I want lower standard deviation, of course, but this K drops more naturally. Okay, so that's what's going on there. So let's look at again the statistical strength allowable. You're going to design to this strength allowable. You're not going to design to the average. So, for example, I have testing that I did on the Tensile test machine, and I got 40 KSI, 50, 30, 50. I don't want to design to the average of this. The average of this is 170. This is 170 divided by 2, which is 85. Well, divided by 4, which is 20 something, right? 22 point something. So I don't want to design to that number, right? It's not logical to design to that value. So, right, this is 170. So 170 divided by 4 is close to 42 or so. I don't want to design to 42. I want to design to a minimum statistical value. So I use statistics instead. And the statistics are going to help me design a structure. And you can see I use A basis allowable at 99% population. And this is, I'm going to do it with 95% confidence. This A basis is used for single point catastrophic failure with no load redistribution. I know the average of this data set. I know the standard deviation of this data set. I can find it. All I have to do is find K from a table, and that K is given here. You can see it. So how many samples I have? I have 4 here. So I go here and I see 7.042 A basis. So that's what I plug in here in this K. That gives me the A basis allowable. And I want to design to this. I don't want to design to the average. I can calculate B basis allowable to calculate the average, calculate KB, and that'll give me a strength that I'll design to. Now note that this is a 90% population with 95% confidence that the material, the value of that strength will be greater than the value here. So in other words, if I do this calculation and I got 35, well then have 90% chance that every single testing I do in the future will fall above this value with 95% confidence. And I want that. I want the highest strength possible. I want to deliver the highest strength possible. This also explains why the A basis is more conservative. This value typically will be lower than this one because A basis is more stringent. It's 99% of the population versus B basis, which is 90% of the population. And I'll do an example. Here's the table for A basis and B basis and A basis. And this one came from the CMS 17 handbook, the Mill Handbook 17. So again, here's an example of number of batches, number of panels, and number of specimens, and the different tests that were done as an example to get the data that you need. So when I'm talking about B basis is that your test data is going to have a normal distribution with an average here. Well, the 10th percentile is down here. You're designing for B basis down here. That's what it means. Let's look at this example. I have 6 samples. The average of this data is 116. I have 6 samples, so I go here to this table. And for 6 samples, I find that it's 3, basically 3, the scatter factor. So I plug it in here. The standard deviation can be calculated by Excel really quickly. I get 8.82. So I design to 90 KSI. I never design to the average. I don't design to the lowest value. I design to 90 KSI because that's going to protect me against any variabilities in the future. We got that. So you're going to encounter situations where you need to estimate the value for a particular condition. Here what you see is the y-axis. You see the B basis strength. The x-axis has a temperature. And I want to figure out the value at this point. So you could estimate that. So I measure this one, this one, this one, this one. Just draw a line from this one to this one and make this line parallel to these two. And so that we can get this point here. The next thing to do is if I want to find testing, if I want to find values, say at 100 degrees, I just draw a line here and then I can then determine at wet conditions what is the allowable I need? And if it's dry, what is the allowable I need? You typically design for hot, wet conditions, elevated above room temperature. That's what R means. Room temperature is elevated. T is temperature, D is dry, W is wet. I want to design above room temperature. Most likely you'll have to. And also for moisture. These composites are sensitive to moisture. You can see that here. The B basic strength value was impacted by moisture, as you can see. When I increased, when I put moisture, you can see that this data point dropped down here. You can also see how when I increase the temperature, the strength also decreased. So various things to consider. They're very powerful and they need to be done. You may have to then use the allowable calculation, the factor of safety, the stress from the finite element model or hand calculation to calculate the margin of safety. And what all this is saying is if your allowable is greater than the factor of safety times the stress from the model, you're good to go. The factor of safety is included for the purposes of accounting for build-to-build variability, uncertainty in the analysis, manufacturing process variability, and unknowns. So here's an example. These are the values for a particular program X. Program X has 1.5 factor safety. The stress was predicted to be 72 KSI. The B basic strength 90 KSI. Very simply, just plug it in and calculate the margin. The margin came out to be negative 16%. So most likely you have to redesign. In some cases, you may have to ask the question, do I really need to redesign? Maybe it was an artifact of the model. Maybe it was something was weird about the allowable. I want to go back and revisit that. Maybe I need to tighten the quality control of my composite when I make it. Let me go and study that. Maybe I can make this better. The answer is not always changing the ply angles. The answer is not always adding more plies. The answer could be simply repeat the test or look at what could have gone wrong. That's one possibility. And so people use these probability calculations. That's one approach, but the approach I'm teaching this class is not a reliability based, but one based on the A basis allowable, which is tied to statistics, and the B basis allowable, which is also tied to statistics. We're not looking here at anything else other than that. But you can calculate structural reliability. If you have the stress variation and the strength variation, you can come up with the probability of failure, which would be the intersection of these two. I encourage you to read chapter 8 from the Mill Hammock 17. It goes through the statistics. Some warnings to consider. Every program has different requirements. Statistics will never replace quality control. You need to really ensure that the distribution data is, what is it? Is it viable, normal? Depending upon that, you may have to adjust. I also then want to conclude a little bit with micromechanics and micromechanics. I covered that in the previous lecture, but I want to do it really quickly here. The mechanical behavior composite is traditionally evaluated on the microscopic scale. Micromechanics, though, tends to quantify the interaction of the fiber and the matrix on a micro scale. And micromechanics tends to treat the composite as a homogeneous material without really going to the micromechanics. What we've done in this particular lecture is to show you how to translate a micromechanical behavior to micromechanical behavior. We did that in the previous lecture. And it can be looked at. So continuing on, I want to look at the micromechanical behavior of the lamina. Lamina tends to be linear elastic, stress-free, fibers, irregularly spaced, ideally. The matrix is isotropic. These are idealizations that we're talking about, right? And we want to understand what it looks like in the volume element. So when I look at a composite, it looks like this. And a simplified element of that looks like this, right? So I want to characterize the properties at this level. And the questions I discussed in the previous lecture is that the modulus in the axial direction, or E11, which you can measure through testing, you can then also estimate this through analysis. And pardon me. And you can estimate that because if you have the volume content of the matrix and the fiber volume content of the fiber, and you know the modulus of the matrix and the modulus of the fiber from the vendor, you can come up with the actual modulus. You can also look at the transverse direction, and I cover that. In the transverse direction, this will be the formula. There's other properties that can be used, estimated the rules of mixture. You can estimate Poisson ratio in the same way. It's going to be off. In some cases, a lot, but sometimes you have to start somewhere if you don't have the test data. So it's okay to do that as long as you know that you have to go back and get the data. As you're reading to understand those assumptions. Here is a list of mechanical properties of typical unidirectional composites. You can see here S for epoxy with a fiber volume content of 62%, T300, Kevlar, and S2 glass. Next, you see the density, ply thickness, and so forth. E11, E22, Nu12, G12, tensile strength, compressive strength, and so forth. All these testing can be obtained using the ASTM standard I had previously discussed. Tensile strength of unidirectional lamina, I already talked about this, works reasonably well, but if you try to apply this formula to strength, it does not work that well. And the reason is because modulus is an intrinsic property, while stress is an extrinsic property. It is microstructurally sensitive. Factors that can impact the strength of composites is fabrication condition, residual stress, work hardening, and phase transformation of the constituents. And so yeah, in this lecture, what we've done is learn about how to populate, really, because we need that for the analysis. We learn how to characterize the material properties using the ASTM standards and how to support that through testing that can then inform this constitutive law equation here. Not only that, can calculate strength. I showed you that you can actually get strength. You can get strain to failure. You can also get other parameters that are required for the calculations. Um, with that said, I appreciate your attention, and I will see you next week for a new lecture.